Hey Yash, I had a flat tire recently?
Really? How'd you fix it?
Well, I took it to the shop, they patched it up and sent me home. How else do you fix it?
Well, you could use Fix-A-Flat.
Fix a flat? What's that?
Oh, nothing. It's just a can of compressed volatile gas.
That sounds a little dangerous.
Oh, don't worry about it. You can reinflate your tire real quick.
So how does it work?
Let's get into that with this question. So the question is, a thermodynamically interesting problem is to analyze the fundamentals behind the product called Fix-A-Flat. In reality, this product is a 500 milliliter can that contains a volatile compound under pressure, such that most of it is liquid. Nevertheless, we can make an initial approximation of this process by treating the contents of the can as an ideal gas. If the initial temperature of both the compressed air and the air in the tire is 300 Kelvin, estimate the initial pressure in the compressed air can necessary to reinflate one tire from 1 bar to 3 bar. Also, estimate the final air temperature in the tire and in the can. For the purpose of this calculation, you may assume that air is an ideal gas with a Cp over R value of 7 over 2. The tire does not change in its size or shape during the inflation process, and the inner tube of the tire has a volume of 40,000 centimeter cubed. We will reconsider this problem with liquid contents after discussing phase equilibrium in a pure fluid.
So using the question, we can take away some given information. For the tire, we know that the initial temperature is 300 K and that the volume is 40,000 centimeters cubed. And we're also told that there's no change in the shape or size of the tire. And for the can, we know that the initial temperature is also 300 K and the volume is 500 milliliters. We are told to treat the components in this problem as an ideal gas. So with air as an ideal gas, we have a Cp over R value of 7 over 2. And if we simplify that down, we get that Cp is equal to 7R over 2.
All right, to begin, so in part A, if the initial temperature of both the compressed air and the air in the tire is 300 Kelvin, estimate the initial pressure and in the compressed air can necessary to reinflate one tire from 1 bar to 3 bar. We can begin by creating an energy balance with a sum of the internal energies equaling to the final internal energies. The reason we do this is because our system is the can and the tire, meaning that the enthalpy leaving the can is the same as the enthalpy entering the tire. Therefore, we can set the enthalpies, N times the internal energy, equal to each other.
We're also able to simplify some terms before we begin this problem because we do have some unknowns. Given that we have an ideal gas, we can change N into PV over RT. This can be useful because we're given a pressure, temperature, and volume, and we'll be able to cancel out terms in the end. We can also substitute in CVT for U. Because we know that delta U is equal to the integral of CV dt, and because we have CV as a constant for each term, it'll be canceled out. So for U, we'll just plug in T, and this T will cancel out with the PV over RT from above. So this will leave us with the pressure and the volume initial in the can plus the pressure and volume initial in the tire will equal the pressure and the volume final in the can plus the pressure and the volume final in the tire. And something we can do before we begin the problem is to convert our units. For the can, we know we have a 500 milliliter volume can. We'll convert that to 0.5 liters. And for the tire, we have a 40,000 cubic centimeter can or tire, and we'll convert that into 40 liters. Now we can solve for our initial pressure. So this is the equation that we had before. We will solve for our pressure initial in the can, plugging our values from above. We'll get that the pressure initial in the can is 163 bar.
For part B, we also want to estimate the final air temperature in the tire and in the can. So to do this, we can start by finding the final air temperature of the can. To do this, we set delta S equal to 0. We do this because if we're only looking at the can, we can put whatever is lost to the surroundings back into the can. Therefore, this process is reversible, so delta S is equal to 0. For ideal gases, we can use the equation delta S equals 0 equals the Cp of natural log of T2 over T1 plus R times the natural log of P2 over P1. Simplifying this equation and plugging in our T1, P2, and P1 values, we get a final temperature in the can of 95.8 Kelvin.
And for the tire, we can do a molar balance of what is going in and what is coming out, which is the equation you see at the top. For the can, we have solved for the initial pressure of 163 bar. We have 0.5 liters and 300 K. And final, we have 3 bars, 0.5 liter, and our solved temperature of 95.8 K. For the tire, we have initial 1 bar, 40 liters, and 300 K. And final, we have 3 bar, 40 liters, and we're going to solve for T. Plugging in our values into that equation, we're going to get a temperature of 390 K. Thank you guys for watching.